We're now recording. So let's get the slideshow set up from the current slide. Actually, we did this slide, well, let's turn on the projector. We did this slide last time. Let me go over this for you just briefly. First, my apology. This has been a crazy week so far. In class on Monday, we decided, y'all told me you did want to test on chapter 5. Okay, only really covered 4 sections of it well, so I was going to do 2 questions on whatever that was, 5-4. Is that where we began? I mean, we began a little earlier, but we just sort of scoped around until we found where you left off. 2 questions on 5-4, 2 on 5-5, 2 on 5-6, 3 on 5-7, and 3 on 5-8. Okay? So I planned to do that Monday afternoon. Well, Monday afternoon they called a meeting that I had to go to on the Birmingham campus from 2 to 4. So the meeting that one got over a little bit early, but I didn't have the stuff I needed to do the test. Okay? So I couldn't do it then. I spent the rest of the afternoon, and I had to meet somebody later on Birmingham campus anyway, so wasted. Okay? Then yesterday afternoon, they had us back on the Birmingham campus from 3 to, it's supposed to be 3 to 7, but nothing was happening, so I left about 5:15. I tried to work on it some then. Like I said, I think I passed out 1 piece of information on CLEP for Math 100. That's the only thing that they had me over there all afternoon for that. But I carried the test bank, I carried this computer, but unfortunately this computer only has Word on it. And Word's equation editor is awful. I mean, well, it's probably pretty good, but I'm so used to WordPerfect. And the WordPerfect package I have is decades old. And their equation editor decades ago was far superior to what Word's equation editor is today. I was working like crazy getting one problem typed in the equation editor. I mean, it's so awkward. It's such a miserable thing to work with. Of course, I wasn't used to it. It was part of that. But even once I got used to it, it was miserable. So finally, I got 1 question typed, and that's all. I was going to try to work on it last night some, but I just didn't have an opportunity. So, this afternoon, okay, they're not calling any more meetings that I know of. They have something they expect us to be at until 2 o'clock, but I'm in class until 1:55, so I'll go down and eat lunch. Well, it's the people from ITT Tech, they closed, they just shut down at the first of this term, and all those people didn't have anywhere to go. Well, their fall term started after ours did, so they couldn't come here, but they can come for second mini term. So we put a lot of classes out there for them. We don't know how many of them we'll do, but we're going to try to get as many as we can. So that's what we're doing. That was what the meeting was Monday. The recruiting was yesterday, and we're doing it again today on this campus. So I'll be probably not in the office over my lunch hour, which I usually am, but then I'll be back in the office after 2. And so I'll try to get your test done. I'm doing it in WordPerfect. I'm going to forget that first problem. It'll be so much easier to retype than go back. So anyway, my sad story. Okay, didn't like the violin music. Okay, now we finally have come up, but let me hide the presenter view because for people watching at home, if y'all two or somebody else. Sorry, my head's all clogged up today. Okay, I think it's ready to go. Any questions on anything we've done up till now? Okay, we're in section 6.1, and this figure is toward the bottom of page 335. This was the problem we did, okay? Example 3, okay? Broke it into pieces and did each one of them separate. Now what I want to suggest to you here, and this is what's I think I could just barely get everything on one slide here. Okay. Now it's cutting off at the end. It does this periodically. I don't know why. You see it's moved the whole screen down here. This used to be at the bottom. Now it's here. It just does whatever it wants to. I can't help it. Sorry. So what we did before, we split this. We're trying to get the area in between these three curves. These are lines, and that's a curve. Okay, but we call them all three curves. Okay, and what we did before, this is what last time, the area, split this into two pieces, the A piece and the B piece, because in the A piece, you're going from this line to that line, so it's this minus that is the length of that rectangle, you know, your dx here and your rectangle there, okay? But then from here, the B piece, your dx is your width and your height is 8 over x squared minus x. That's the height here, and that's what you integrate for that part, the difference between those two. And we did the integrations with it. Now, I was kind of expecting, or wouldn't have been surprised if somebody said, in fact, I think I may have mentioned it, could you do dy's rather than dx's? And that's exactly the next thing we're going to do. Well, in that case, you would have to do your dividing line right here, okay? And then you would do this piece and that piece, okay? In the lower piece, it would be x minus 8x. That would be the length, the width would be dy, and the length would be this line minus that line, okay? That wouldn't have been bad. But the upper part of that would have been this minus, okay, let me back off, sorry, I said that wrong. Since you're doing a dy here, that's the width, you have to get your equations in terms of y. X is a function of y, not y is a function of x. See, that works just perfectly the way it is now for dx because you got your y's in terms of x. If you chose to do dy's, then you need x in terms of y. Well, this one's easy. X equals y. Y is equal to x, x equals y. This one is not bad. That would be x is equal to y over 8. Okay? So this length here would be y minus y over 8 dy. That would be the first part, the lower part of that curve, the area. The upper part, though, you'd have to get this as a function, x as a function of y. And that's a little messier. X squared would be 8 over y, and then you have to take the square root. And since we have y's being positive here, and x is positive, then you can just do the positive square root of 8 over y. Okay? And that would be a messier thing to do. So that's why we do our dx. This problem is just set up for it. But at the bottom of that page, bottom of page 335, what do you do if you're integrating along the y-axis? So what if we're given x as a function of y? It wasn't something we had to do. We were actually given that. What is the meaning of the integral from, let's see, because I know it's going to skew things, I'm going to do it like this. Yeah, still, so I could have gone back the other way a little bit. What if you were doing the integral? See if my pen is, I don't think my pen, yeah, that's right, I can't, right. I'm supposed to be able to find my pointer down here, and they're not showing up. So I have to do it this way. What if you had x as some function g of y? Okay. What then would be the meaning of the integral from c to d of g of y dy? Okay. Well, here is one, right here. In fact, there's two of them. Here is a function. X is some function of y. X is y squared minus 9. Over here, you have a difference of two functions. X on the right is g of y. X on the left is h of y. both of those are functions of y, not functions of x. Okay? See, x's would be kind of hard to do in this case, okay? Because you have to solve this for y and then do the limits here, and the limit there, and limit there. I mean, it's messy because you see those aren't even functions of x. You have to take them piece at a time. So what if you were given that? Then what that would mean if you're going from c to d, dy is your increment here, that's your delta y here, that's your dy, and then your difference of one function to the other. This one doesn't have a difference, it's just g of y. G of y dy. Okay? Now the example they show here is the integral of x equal y squared minus 9 from minus 6 to 6. That's your c, your d, and your function is y squared minus 9, g of y, and you're doing increments in dy. Now, what that gives you is the signed area. So any areas that are to the right of this are positive areas, to the left are negative areas. And you're summing them all up, these will be negative, these will be positive. Well, guess what? Whatever these two add to, subtract that from, and you wind up with a smaller area than you would otherwise. If you want total area, then what you have to do is make this 0 minus. Okay, you're doing functions of y. And you're doing x equal 0 minus x equal this. So that would be the minus, that would be 9 minus y squared from minus 3 to 3. Y squared minus 9 from minus 6 to minus 3 and from 3 to 6. So you just split it up and do it that way. That's what we mean by using function of y. Integration. If you think about your increments and your lengths, it'll all come out in the wash. Okay? Pretty much. Sorry, I'm all choked up here. So let's do this one that they said. They didn't make us do it, but what we're going to do is let's actually do this one right here. The function here, our g of y, is this. So we're going from, like I said, your c is negative 6, your d is positive 6, okay? And you're doing the function, which is y squared minus 9 dy, okay? Now just to get what you're doing here, you're doing dy, so your increments are along the y-axis, and you're doing y squared minus 9 minus 0 here. You're doing y squared minus 9 minus 0 here, but that's going to give you a negative amount, and y squared minus 9 minus 0 is going to give you a positive amount there. Okay? So if we just do it straightforward, you understand this is going to be total area. This will be the signed area. So the pluses count positive, the negatives take away. Now, before we get started, I'm plumb lazy. I think I've told you all that's a requirement to be good at math, right? Not really. Okay. What do you notice about this function, especially in regard here? The part down here is exactly like the part up here. It's symmetric about the x-axis. So rather than doing negative 6 to 6, let's just do 0 to 6 and double it. That should work, shouldn't it? Anytime they're symmetric like that, you can do. So I'm going to be really lazy and do twice the integral from 0 to 6 of y squared minus 9. Yeah. I should have minus 9 dy. I'm sorry. My head is clogging up on me. I don't know why. I hate doing this. Sorry. I went by the restroom twice between classes to clear out, and I'm still clogged up. Now, and that's a zero down here, by the way. It's ugly, but it's true. Can you do the integration? Antiderivative of y squared, y cubed over 3 minus 9y. Evaluate that from 0 to 6. Okay? And that would be 2 times. Anyone know what 6 cubed is? You can use your calculator if you want to, but it's 36 times 6, right? 216. So 216 divided by 3, that would be 72. Okay? Minus, and 9 times 6 is 54. Okay? I can do the 0 part. That's 0. Okay. Y'all don't have to worry for that one. Okay, and that would be 2 times 72 minus 54 is 16, and that would be 32. And sure enough, 18, and that would be 36, okay, if I could add. Why my and 36? Okay, good deal. Okay. You see how that works. Now, what's more, as long as g of y is always greater than h of y, as in this deal, then you can do the area between two curves. As long as g of y is always greater than or equal to h of y, you can do the area between two curves. Do it the same way. Choose your dy's. dx's would be miserable here. Okay? So choose dy's, and you have to have this as a function of y, g of y, this is a function of y, h of y. The dy is the width, the length is g minus h. And integrate that from c to d. That gives you your total area. All right? Now, more generally, okay, what we call this function here is a horizontally simple function. Okay? I like being horizontal as much as possible, but that's pretty simple. But that's not the same thing we're talking about here. This means you can do increments in dy, the horizontal increments, and then make it really easy. Okay? Let's go back. See, this would not be vertically simple at all. Nowhere. This would not be vertically simple. I mean, this piece alone would be vertically simple. This one would not be. This one would be. Okay? But altogether, they wouldn't be. Okay? This one's horizontally simple, not vertically simple. Okay? You go back here, again, in the pieces, vertically simple all along the way. Horizontally, not bad, but you still, they're horizontally simple. You could do it that way, but you have to change the function x to the function of y. And that's what gets messy in that way. So you can still do it, and they are either horizontally or vertically simple. Okay? And that's what they're talking about here. More generally, if g of y is always greater than or equal to x of y, as in 8b here, then the graph of x of equal g of y lies to the right of x equal h of y. In this case, we write x to the right, g of y, x to the left, h of y. We call that region horizontally simple, since every horizontal line that intersects the region does so in a single line segment or point, such that the left endpoint is on the curve x of y and the right is on left is on g of y and left on h of y. Horizontally simple here, fairly simple here anyway. Vertically, not. You see, that's not vertically simple. They're on the same function there. Okay. So, the area between the graphs. See, how do I want to do it? I think this is how I want to do it. So it'll all show up on the slide. Area between the graphs will then be the integral from C to D of x to the right minus x to the left. That gives you the length, dx is the width. Sum all those up from C to D. You got it. So that would be g of y minus h of y. That's the length times the width. Sum those up. You got it. That's what integration does for you. Does that make sense? Do you like to think of it that way? Okay, I think we can do example 4 here. Oh, I see. Okay. Yeah. Okay. This is example 4. There was another figure in my text that's not on the slide, and that was figure 9. And that's a horizontally simple. Notice vertically it wouldn't be simple. Horizontal would be simple because the line that goes, horizontal line goes from one graph to the other from between the limits C and A and B. For some reason, put A and B there. All right, here's our problem here. Calculate the area enclosed by the graphs of h of y. I'll blow this up for now, but it won't stay blown up. You know that. Okay, zoom in. Zoom in. About like that. Okay. The area enclosed by the graphs of h of y is equal to y squared minus 1. That's the red line. X equals y squared minus 1. And g of y is the blue line. X equals y squared minus 1/8 y fourth plus 1. Now, they didn't write those in very nice order, but it's okay. You know, we can deal with that. All right. Now, what does it say? Calculate the area enclosed by the two graphs. Now, they've given us way too much already. They drew the graphs for us. Thank you very much. I'm glad I didn't have to draw them. This one wouldn't be hard to draw. Notice it's y squared, x equals y squared would be that parabola. Shift it 1 to the left, and you got this parabola. That's pretty easy. The other one's a little bit messy, okay? But it's all doable, okay? Now, what we have to do first is find where the area is. And they've shown us on the graph, we have to determine what are the limits. Now, which way you want to do? You want to do dx's here, or you want to do dy's here? Is this vertically simple? No. Is it horizontally simple? Yeah, it is. Every horizontal line goes from one graph to the other. That's horizontally simple. So we want to do dy's. Okay? So since we're doing dy's, what are the limits on the y? We can look at it and have a pretty good idea. Let's actually, how do you calculate this? If they didn't draw the graph for you, which on the test, guess what? They're not. Okay? I'm not. You know, you're going to have to figure this out on your own. What will you do to determine the limits on that? Say again? Now yeah, set them equal to each other. Oh, that's why I couldn't do it. Okay. So, y squared minus 1/8 y fourth plus 1 is equal to y squared minus 1. Okay? How would you set those equal to each other? Yeah, move it all one side or the other. Which way you want to move now? To the right or to the left? Or stand up, sit down, fight, fight. No, okay. I like to go to the left. I like that. Let's add 1/8 y fourth to both sides. Okay. We would also have to subtract y squared from both sides. and subtract 1 from both sides. Okay, this goes, that goes, that goes. So this side is our 0 side now. This would be 1/8 y to the 4th. The y squareds actually disappear, and you have minus 2. Okay? Now, I think the first thing I would do here is, what would you do? You tell me. What is it you don't like most about the way that looks? Anything? You love it the way it looks. Oh, you want to swap sides? Okay, we can do that. 1/8 y 4th minus 2 is equal to 0. Is that what you meant? That maybe wasn't what you meant. Oh, you're going to add 2 to both sides. You can do that. 1/8 y to the 4th is equal to 2. Yeah, add 2 to both sides. That works. Ah, very good. I thought you would jump right all over that. What do you not like about the way that looks? That fraction. Most of you don't. Y'all love fractions. I forgot that. Y'all are good math students. You love your fractions. Multiply both sides by 8. So 8 times this and 8 times that. What does that give us? Y 4th is equal to 16. Okay. Now, do you still like it this way, or you want to do something else? Can you two? Huh? What's that? I still can't hear. Okay. Again, my hearing is so bad I can't make it. Yeah. What raised to the 4th power is 16? Is that what you're saying? Okay. And what would that be? 2. Or, yes, plus or minus 2. And sure enough, that's what it looks like here. That's where it's minus 2, and this is where it's plus 2. Okay, yeah, we've determined that. All right, and those are y values, y equal negative 2, y is equal plus 2. Very good. I was kind of expecting you to go back to the other way and do y 4th minus 16 is equal to 0, y squared plus 4, y squared minus 4, y plus 4 doesn't factor. Y squared minus 4 factors is y plus 2 and y minus 2. Yeah, that would give it to you too. But this is fine. If you see that, that's perfectly fine. Okay, now, are you ready to integrate then? You got the limits, y is equal to plus 2 or minus 2, or do we? What do you notice about this function? It's symmetric. He's lazy, I can tell, okay? So what might we do? Just do 0 to 2 and double it, because the area up here is the same as the area down here. Both of these are even functions in y, so they are symmetric about the x-axis. So what we're going to do is then the area is equal to twice the area from 0 to 2. Now, what's our difference here? This is where you have to be careful. Okay, yeah, that's your right-hand function. You write that first, and they write it as y squared minus 1/8 y to the 4th plus 1 minus the second one, the left-hand one, and what's that? Y squared plus 1. Very good, okay? And then you have your dy, because that's your thickness, okay? Again, your y squareds go away, okay? So now we have the limit, the area is twice, okay? Can we integrate that? Negative y to the 5th over 40. Oh, I love these fractions, don't you? Okay? And you combine these two and you get plus 2y. And we're evaluating that from 0 to 2. That's going to be 2 times. Sorry. All right. What's 2 to the 5th? Anyone know? 32 over 40. That's going to be a minus 32 over 40. Plus 4. I'll do the zeros. Okay, done. Okay. And what does that give us? Well, let's simplify this a little bit. Well, we'll go into both of those. 8 will go into that. 4 times 8 will go into that. 5 times. So basically we have, doesn't matter how you do this. Do you like mixed numbers or do you like fractions? Doesn't matter. Let's keep it in fractions. How many fifths is 4? 20 fifths. So that would be 20 fifths minus 4 fifths would be 16 fifths. So this will be 32 fifths. Okay? Boy, my screen just was really scratchy there. All right, that's what we got. Let's see what they got. Yep, 32 fifths. Good for them. All right, good deal. Any questions on that? You see how that works? Okay. Okay. Yes. Okay, it stayed negative. This negative 1/8 y4 became negative y5 over the, you increase that by 1, divide by 5. You already had 8 in the wrong side. That's where you got this. That negative. Okay.
But it's already negative, right?
What?
It's 1/8 is negative, 1/8.
Yeah, 1/8 y4 is negative.
Okay.
So when you integrate that, you keep the minus sign. You still have the 1/8 here. And when you integrate this, you have y5 over 5, right?
Yeah.
Okay? And 5 times 8 is 40. So you have negative y5 over 40.
No, what I'm confused about is y squared. That's positive y squared.
Right.
And the negative y squared.
Right.
When you cancel out,
Yeah.
what happened to the negative in front of the y squared?
Okay.
It's going to go?
A plus y squared minus y squared is 0.
Oh, yeah.
Got it. Okay? Yeah. So plus y squared took care of it. Okay. And then you have plus 2, and we integrate that as plus 2y squared. Integrate that from 0 to 2. Good question. Okay. Now, let's see. Do they have example? No, they don't have example 5. This was in the new edition. They have example 5 that wasn't in the old edition, and I really hate that because I wish I had the a whiteboard to use on it. I mean, they had already done the graph, so I'm going to have to do the graph. So what I'm going to do first is erase all stuff on the slide and just ignore this one and come up here and draw this. Find the area of the region that is bounded by the 3 curves. Y is equal to x squared. Y is equal to x minus 2 squared. And y is equal to 0. It's not much of a curve, but it is technically a curve. Okay. So we have to draw a picture. This is more like your test than homework questions will be. They don't always have the pictures accompanying. All right, so let's draw our axes here. Okay. Y is equal to x squared. Let's tick off some. Okay. So, how would you draw y is equal to x squared? Yeah, it's a parabola, 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4, 3, 9. Yeah, that's just a good old parabola here. Not a very pretty parabola, but it's a parabola, supposedly. So, x minus 2 squared. What would that be? You want me to put that in a different color? What color you want? Red? Is that what you said? Okay, you like the dark or the light? The light. Okay, we'll do that one. Okay? So this one will be in red. How do we do that? Go which way to? Over. Which way is over? Right. Okay, very good. Right there, and then you'll do that point and this point, and this point and that point. So here's the second parabola. Looks just like the first, it's just been translated to the right twice. Okay? How about y is equal to 0? Where's that? Not the y-axis. X-axis. Y is equal to 0 is the x-axis. So basically what we're talking about here, now do you want me to fill in this in red or would you rather have something lighter? How about the pale yellow? Okay, so basically we're talking about this region right there. Boy, pretty small, huh? Now the question is, which way do we want to do this? We want to do dx's or dy's? The first part of me, when I looked at this, thought, this is y as a function of x, y as a function of x, y as a function of x. Let's do dx's. Except you're going to have two pieces here. And that's fine. It's perfectly fine to do it that way. But if you changed it, then you have, y'all give me another color. Green. How about the dark green? Okay. If we did this way, you see this is horizontally simple. Okay. Vertically, it was simple in two pieces, and your functions are simple. This is horizontally simple, and you just use the two functions. You just integrate from 0 to 1, because that's where they intersect. But you've got to change both of your functions, and these aren't impossible to do, but what you would do then would be x is equal to the square root of y, and we use the positive because x is always positive here. And here we'd have x minus 2 is equal to the square root of y, again using the positive there, and then add 2. Okay, so x is equal to 2 plus the square root of y. So those are the two. All right? Now, actually that works out pretty nicely, doesn't it? Because when you do your subtraction, what is your integral then? You want it back in black? Okay. Well, I don't know why. All right. The integral from where to where? If you're doing dy's, 0 to 1. Okay, that's simple. And then what's your length of that? I should have done this one in red. But it would be the rightmost one minus the leftmost one, which would be 2 plus square root of y minus the square root of y. Boy, this looks like it's going to be way too easy, doesn't it? dy, that's your thickness. That goes away. And what does that give you? Integral from 0 to 1 of 2 dy. Oh boy, that's a hard one, isn't it? What's that going to end up being? 2y evaluated from 0 to 1, and that's tough. 2. Okay. That looks way too simple. We must have done something wrong. And obviously we did, because I got 2/3. Okay. Okay, let's go back here a minute. They got a minus square root of y. Why did they get that? Yes, sorry about that. That was my error. This function right here, the red one, this side is y is equal to, if you broke this down like I did here, I said we're dealing only with positive x's, okay? No, every x was positive here. That was my error. Okay, here's what it should have been. X minus 2 squared is equal to y. Okay, sorry, I botched it. When your x is over here, that's your positive square root. When your x is here, that's your negative square root. So when you did the next step and said x minus 2 is equal to the square root of y, I said, well, that's positive. No, it isn't. That's your negative square root of y. For these values of x's over here, that's your minus. Okay, so that should have been the minus square root. This one was positive. That one was minus. Then you add 2 to both sides. X equal to minus the square root of y. So this would have been, I thought that was looking like it's way too easy, and it didn't make sense. That's a minus, then a minus, so this gives you, let me wipe out these. Okay, sorry about that, folks. Okay, that would be 2 minus 2 root y dy. Now, I don't like to integrate radicals, so how do I suggest you do that? 2 minus 2, well, why am I carrying around all those 2's, okay? Since you got 2's in there, whoops. Yuck. Let's factor out a 2. Make it 1 minus y to the 1/2 dy. Okay, let's integrate that. 2 times antiderivative of 1, y minus y to the 3/2 times what? 2 over 3. Yeah, 2/3. Right, perfect. Okay, and we'll evaluate that from 0 to 1. Now, how did that become a 2? That was just sloppy. Okay, that's just a 1 there. Okay. You should have caught me on that one. Okay. That would be what? 2 times 1 minus 2/3. 1 minus 2/3 is 1/3, and 2 times 1/3 is 2/3. All right, got it. Sorry about that. Okay. And the reason for that is when you take the square root of this thing, it's not positive square root of y. That would have been this side. You're going from this side, which is a negative square root of y. So that's why that was a minus there. So I should have gotten rid of, so do this even though the cat's out of the barn here, so you don't keep cats in barns, okay? Okay. Well, that Okay. Anyway, that's done. That finishes section 6.1. Okay. They do have a little summary there, and if I remember right, y'all want to do the preliminary questions, right? Yay or nay? Yeah. Okay. So let's clear all the ink. I'm sorry I'm having to do this. They're not giving me my little icons at the bottom that we had last time. So, question. What is the area interpretation of this? It says, let me go back to black here too. Okay. The integral from a to b of f of x minus g of x dx. If f of x is greater than or equal to g of x everywhere in the region between a and b. So what's the area interpretation of that? Might have to draw a figure. So you can draw f of x anywhere you want to. That could be f of x. G of x could be something down here. It doesn't have to be negative, I just drew it that way. That area interpretation would be taking a could be anywhere you wanted it to, too. So let's say from A to B. Let that be B. It would be the area in between those curves. Right? As long as f is always greater than or equal to g. They could touch in places, but f can't cross it. Okay? Always f has to be on top. F could be negative, but g would just have to be more negative. Okay, for every point by point, or at least the same. Okay. Just for fun, let's just see how they answer that in the back. I don't want to be leaving out something they are wanting to emphasize, so let's see if they even say that. Here we go, 6.1. The area of the region between the graphs of y is equal to f of x and y is equal to g of x, bounded on the left by the vertical line x equal a, and on the right by the vertical line x equal b. Just what I drew there. Okay. So if you want to write it out, that's how you write it out. Number 2. Let's just clear all this and start afresh. Any questions? If you have questions, stop me. Okay, number 2 is... why didn't I leave it up there? The integral from a to b of f of x minus g of x dx still equal to the area between the graphs of f and g if f is greater than or equal to 0 and g is less than or equal to 0. Yes, as long as f is greater than g. And if f is always greater than or equal to 0, g is always less than or equal to 0, it's got to be greater than or equal. They could both be 0 at the same time. But yeah, it still is. In my example, my ugly figure, that showed exactly the same thing. I just chose that, but yeah, I didn't have to. So, that was a yes. Yes. Okay. Number 3. Suppose that f of x is greater than or equal to g of x on 0 to 3. Okay. I'll erase all that. Okay. Let's suppose that f of x is greater than or equal to g of x on 0 to 3. Okay. And that g of x is greater than or equal to f of x on 3 to 5. Okay. Express the area between the graphs over 0 to 5 as a sum of rectangles. No, I'm sorry. I was going to say, what in the world is that? I can't read. Sum of integrals. Okay. So you want the whole area, not the signed area, the entire area. So what would that be? As a sum of integrals. What would be your first integral? That would be 0 to 3. Alpha of x minus g of x dx. And what would be your second integral? 3 to 5 of g of x minus alpha of x. Always do the one that's greater first if you're wanting the actual area, and that would be dx. Perfect. Y'all are good. Let me make sure the back of the book got it right. Integral 0 to 3, alpha of x minus g of x dx minus, oh, okay. No, they don't. Okay. Back of the book is a little wrong here. They put a minus sign in between there. Okay? Now, if you put a minus sign in there, here's what you would do. 0 to 3, alpha of x minus g of x dx minus integral from 3 to 5 of alpha of x minus g of x dx. Okay? Now, if you wanted to do that, if you wanted the minus sign, then you put the alpha in front. But they did it our way, but changed the minus sign. Unless I'm missing something, theirs is wrong. Sorry about that. But they put an extra minus sign where they shouldn't have, or leave it a plus. And yeah, the way they wrote it, it should have been a plus. Okay. Sorry about that. Okay. That was 3. Let's go to 4. If I'd have known they were going to be getting them wrong, I wouldn't have done it. Okay. Suppose that the graph of x equal f of y lies to the left of the y-axis. So x equal alpha of y is left of y-axis. Okay. Is the integral from a to b, you use c to d there, but it's okay, alpha of y dy, is that positive or negative? What you think? If this is your axis, and here is your alpha of y, x equal alpha of y, from a to b, dy, because that's what you're measuring from, is this thing positive or negative? That integral. Yeah, it's negative if, okay, now, okay. If, this is a big if here, if b is greater than a, then this is negative. Of course, if a was greater than b, then you would, that is negative, because you're integrating 0 minus alpha of y. Put a minus in there, you get a positive area. Okay, so that would be a negative area. I don't think they were trying to be too tricky there, but yes, just say negative. That's exactly right. Okay, now let's do 5. All right, explain what the integral from a to b of absolute value alpha of x minus g of x dx represents. what does that represent? It really shouldn't be a question, but I made it a question. What would that be? Okay, yes, that will definitely always be non-negative. Let's put it that way. Okay, because as long as b is greater than a, let's make that assumption. Then this would be because if f is less than g, then the absolute value of that would be g minus f. Okay, that automatically makes this always positive, and if this is less than that, yeah, this is always. So basically, let's flip this over since we got it up here, and put this part below the x-axis and another part above it. That would be the total area between these two curves. Not the signed area, but the total area. Because if f is greater than g, then you just integrate as normal. And that would be a positive area. If g is greater than f, the absolute value makes that positive as well. So yeah, that would be the total area between the two curves. And it would be always positive. Always positive. The area of the region bounded by the graphs of the functions and the vertical. The area of the region bounded by the graphs of the functions f and g and the vertical lines. Yeah. Just means the total area, not the signed area. Let's do 6. Draw a region that is both vertically simple and horizontally simple. Obviously, that one we have there is not, but there's lots of answers you could have here. How about that one? Would you agree that's vertically simple and horizontally simple? Vertically simple? Yep, that's good. Horizontally simple? Yep, that's good. So yeah, you can come up with many others. They drew one that was a little more esoteric than that. Okay, that would do it. Okay, vertically simple? Yes. Horizontally simple? Yes. Fine. The thing is, if that is a parabola, then to do the horizontally simple one, you have to get x as a function of y, and you've got a square root in there. But we can do square roots. There's no problem with them. It's just easier doing powers, positive powers. All right, homework exercises here. Do either 1 or 3 or both. Okay. Do number 5. Do number 7. Do either 7 or 11. 9 or 11. Do either 13 or 15. Do either 17 or 19. Do 21. Do either 23 or 25. Do 27. Do 29. And then do any of the odds 31 to 47. You got a lot to choose from. Do whichever you'd like to do there. Now 49 indicates you probably need what is that called? Something algebra system. Computer algebra system? Yeah, I think that's it. Computer algebra system. If you don't have that, don't want to mess with it, you could play with it if you wanted to, but whatever. That's up to you. 51 says it's mostly sort of a writing problem. You can read through that, make sure you understand it. Then try to do 53 or 55. 57 requires a computer algebra system, so you decide whether you want to tackle that one or not. 59 is a sort of interesting problem. The figure goes with that, so try to do that one. Do 61. By the way, there is introduced the Gini index. Okay? Now, frankly, I have absolutely no idea what the Gini index is, but if you want to look it up and find out who in the world was Jeannie, and that's not a dream of, but something else. Then see what that is, see how they developed this index, see what it's used for. There's maybe 3 or 4 paper topics right there you could choose from that. And 62 goes into that as well. If you don't find those challenging enough, you could try 63 or 5, but that's completely up to you. All right. Any questions? All right. Not really the end of the show, but this is just to get rid of the screen and X that out, and let's go to 6.2. PowerPoint's been taking a long time to do anything today. And again, it seems like it's taking forever to load, so here it comes. Oh, my head is so clogged up, and I don't know why. Okay. Let's go to current slide. All right. What we're doing now in 6.2 is setting up integrals. This could be volume integrals. We've done set up integrals for area. Now we're going to do volume, density, and average values. So which quantities are represented by integrals? Roughly speaking, integrals represent quantities that are the total amount of something. Okay? Areas we just did. Volumes we are going to do. Total mass we're going to do that kind of stuff as well. There is a 2-step process for computing such quantities. First, approximate the quantity in sum of n terms, and then pass to the limit as n approaches to infinity, okay, to obtain the integral. Summation first, then the integration. We'll use that procedure often and in other sections, so get used to it. All right. First example is the volume of a solid body. And before proceeding, let's recall that the volume of any right circular cylinder. Does anyone know, in fact, when you have a right anything, let me get rid of this. I forgot I was still in presenter view here, so let me get out of that. Okay. Now, what do we mean by a right cylinder? Whatever your base is, the cylinder goes up at right angles to it. Okay? So for any right cylinder, and this is, if your base is this, looks like a Dr. Scholl's pad or something like that, right? If that's your base, then your cylinder goes up perpendicular to that base. So that same Dr. Scholl pad shape goes all the way up completely. That's a right cylinder. Not a circular cylinder. We usually think of cylinders as being circular. This is a Dr. Scholl's foot size cylinder, okay, or something like that, okay? Sort of has a bunion over here, but we can get away from that. Okay, so that's the thing. So what's the volume of that? Anytime you have a right regular shape that you're making a cylinder out of by going up perpendicular, basically, it's the area of the base times the height. That's the volume of a generic right structure, whatever it is. You got some area that's going up at right angle to that area. Is to be the area of the base times the height. Okay? So the volume of this right cylinder, not circular cylinder, but right cylinder, area of that base A times the height A. Okay? Now, most things we're going to hit are not right cylinders. They will look much more like this. But here's where our good approximation comes. This volume has some type of symmetry about it. And that symmetry appears to be along the y-axis. Okay? It doesn't have to be completely symmetric there, but it seems like something is regular about the y-axis. So therefore, if we do a delta y here and do some segment in here, even though those sides are varying, that's not a right cylinder. If you get a small enough slice of that, that's approximated by a right cylinder. Okay? If this delta y is small enough, then you don't see too much. There's a little slant there, but guess what? We can live with that. Okay? That would be approximated by the area of the base. But notice all these bases are different, so you have to come up with an equation or a formula for the area of the base times the delta y height. That has that, then you sum all those cylinders up, these incremental cylinders, and you got the volume of the whole plot. So divide the solid into thin horizontal slices. Later we can do vertical slices, doesn't matter. Each slice is nearly a right circular cylinder whose volume can be approximated as whatever its area is. But there's where the problem comes, figuring out the area of each slice, and that needs to be a function of y, okay, of how high up you are. So that's going to be the issue here. If you're doing dy's, you need to find the area in terms of y as well, and then you can sum those from y is equal to a to y is equal to b. Okay? Does that make sense? All right. So, I should have blown those up. I don't know why I didn't. Been easier to talk about. Let's do this one. All right. Can't get the whole thing on here. I don't know why it's wacko today, but it is. So the volume as the integral of cross-sectional area, let A of y, remember we have to somehow figure out a way to express each of those cross-sectional areas as some function of y, be the area of the can't read the word there. Horizontal. Okay, the horizontal cross-section at height y of a solid body extending from y is equal to a to y is equal to b. Then the volume of that solid body would be this integral from a to b of a of y dy. And really, the only hard part here is coming up with a way to express the area as a function of y. If you can get that done, the rest of it's just pretty straightforward. Okay, so that's where you're going to probably spend most of your effort here. So here's one right here. Now I'm going to blow it up for now, but then as soon as I write on it, it's going to come down. I think this will all show up. Go this way with it a little bit. Okay. Okay. What we have here, calculate the volume V of a pyramid of height 12 meters. So the total height from B here to the apex C here is 12 meters. That's pretty tall, okay? 12 meters, and whose base is a square of side 4 meters. 4 meters here, 4 here, 4 here, 4 there. Now, they didn't say what kind of pyramid, but we're going to assume, because the drawing is like this is a perfectly symmetric square pyramid. Okay, you don't have any, it's a right pyramid too. The apex is perpendicular from the center of the base. Okay, the base is a square. Okay, so we know already that we're going to slice it vertically. So if that's going to be your y, yeah, that's what we're going to let that be your y. We're going to be taking dy's, and for any dy they have here, you need to be able to calculate what the area of that slice is. We know the area at the bottom, 4 times 4 is 16. That doesn't help us any. We know the area at the C is going to be 0 because all the sides are coming together there. And we know since this is a square here and all coming up evenly, that's going to be a square. But what we have to have is that area of this square as a function of y. Okay. So that's where our efforts are going to be. Now, notice where we judiciously put the V, this point B. Imagine that is at the origin. 0, X, 0, Y, 0, Z, but now we're letting Y be up there, so we're not even using Z's. Let's just imagine this, okay? So that's the center. So the base here is plus 2 this way, plus 2 this way, minus 2 that way, minus 2 that way. That's the thing. That's how we get our 4. Okay. What we're going to do, it appears that we're going to let this be the positive direction we're going to deal with. And that starts off as being 2. Well, obviously, this length here is, we know that, 12. 12 meters high. This is 2, and I think they said meters here, didn't they? Yeah, square of, the base is a square of 4 meters, which is a pretty good size base, too. So this is 2 meters from here. Then this is called the lateral distance. If you come out 2, so this is exactly bisecting 2 here, 2 here, 2 here, 2 here. That lateral distance there, we don't know, but that's what determines the dimension down here. So that's also going to be the dimension here. What we're going to use is similar triangles. Okay? And what we know is this is 12 and that's 2. So all the way up, this distance here related to that distance there is going to be a ratio of 2 to 12 or 1 to 6. Okay? So this distance here, which is going to be 1/2 of the side here, S. You can do this any way you want to, but that's how they did it. The side of the square here is going to be S. This distance here is 1/2 S. Okay? Well, if this is 1/2 S, then what we need to do is to relate that to this distance here. Okay? Notice all the moving parts here. Total area, length, height of 12. This is your distance Y above the base. So this distance here is 12 minus Y. 12 minus Y is 12 minus Y. All the way up from the base where Y is 0, that would be 12, to the top where Y is 12, that would be, did I say that right? The base down, yeah, I think I said right. Oh, I'm not giving you the height. Where this Y would be 0 down here because it's 12. Yeah, 12 minus 0 would be 12 would be that height. And then when you're up here at the top, you would be Y would be equal 12, that would be a 0. So yeah, that works. The height is 12 minus Y. Like I said already, the ratio between this and that is 1 to 6. So 1/2 of S is to 12 minus Y as 1 is to 6. Okay? Now they haven't, well, I don't think you really need that anyway. You don't need that ratio. You just need that. So, yes, you do need that, I think. Okay, we will in a minute. So, the area of this square, remember that's the thing of importance here. The area of that square is S squared. Okay? So let's write down what we know. Well, oh, I was wondering where my there we go. Okay. So we know that 1/2 S is to 12 minus Y as 1 is to 6. Okay, it's rather strange, but it's true. Let's do a cross multiplication here and here. Okay, this gives us 3s is equal to 12 minus y. So what we want is, so s is equal to 4 minus y over 3. So there we have the side as a function of y, and s squared would be then 16 minus, boy, this is nasty, 8/3 y plus y squared over 9. Squaring this binomial. That seems really messy, but that's indeed what we got. We got the area of this, of any square there as a function of y. Okay? Right? All right. Now, I don't think they do anything else with this except that. Okay? And then our formula, the volume, is equal to the integral. And what is our y going from? Since we're doing dy's, what is our y going from? At the base, your y is, there it is. Y is equal to 0 to y is equal to 12. Right? That's your y's. Okay? You're doing dy's. And your area, this is your area of any one of those squares as a function of y. Okay? Now, they, I think rather smartly, did some things to clean this up a little bit. Let's go on and factor a 1/9 out. I think that's what they did, if I'm not mistaken. Yeah, they do. So let's factor the 1/9 out so we don't have to worry with that. When you factor out of 1/9, that's going to give you a y squared minus, factor out of 1/9, then you're going to have to multiply that by 3. So that's minus 24y plus whatever that is, 144. Okay. That's your integrand. Okay. Now, interestingly, they got the same thing a different way, but this will work. Okay? Let's do the integration. 1/9 y squared, y cubed over 3 minus 12y squared plus 144y evaluated from 0 to 12. Okay? Pull out the calculators. I don't know what 12 cubed is. Okay? 1/9. We might be able to live without it, but that'd be 12 times 12 times 12 divided by 3, so that'd be 4. That'd be 144 times 4, 16, 256, no, 656. Is that right? Boy, y'all must be good. You come to a calculus class with no calculator. That's confidence, folks. 12 cubed divided by 3. I probably botched it up. Oh, it's 556, isn't it? What did you get? Oh, you did the final answer. I think it's 556, isn't it? 576, something like that. Okay, 576, I can't write either, minus, and 12 times y squared, 12 squared, that's 140. You do that one too. 144 times 12. Oh, but guess what? Hey, I can do this. Look, watch this. Watch it. It's 12 times 144 plus, that's a minus. This is 144 times 12. Guess what? That adds to 0. Okay? I did that without a calculator. So it looks like 576, 1/9 of 576. Let's see. Yeah, 9 will go into that. 9 will go into 57 6 times. Huh? 64. So that looks like 64 cubic meters. Oops. Okay. Is that what they got? Look at them. They got it right. Okay. They went about it a slightly different way. Still works. Any way that you can get that, you can go with it. Okay? Now, I can't see the time. How we doing? Huh? Almost 11? So we got at least 10 more minutes. More than 10 more minutes. Okay. And by the way, it says this agrees with the result obtained by the formula V is equal to 1/3 area times the height. Let's see if that works. And by the way, you'll see that in the front of your book, I think. No, they don't have it in the front of the book, do they? I thought they were listed under geometry. It's a lot like your cone, 1/3 the area of the base times the height. Same thing works for pyramid. So let's see if that works here. The volume is equal to 1/3 the area of the base times the height. Be 1/3 the area of the base was 16 square meters times the height 12 meters. 3 will go into 12 4 times 16 is 64 cubic meters. Yes. That was the easy way to do the problem. But we wanted to use calculus, didn't we? Yes. Okay. Go for it. All right, let's look at number 2, example 2. Strange looking figure here. Compute the volume V of the solid in figure 4, whose base is the region between the inverted parabola, y is equal to 4 minus x squared. Let's see, for right now, let's blow this up so we can see it maybe just a little bit better. Okay. Here is the base. This is your x-axis, your y-axis here. And the base is the inverted pyramid. Y is equal to 4 minus x squared. Okay. Yeah, there it is right there. I'm trying to find it. 4 minus x squared. Y is equal to minus x squared would be the pyramid down here at 0. Translate it positive 4 up. There you get that pyramid. Okay? So there's your base. Okay? Now what you're doing with that base, whose base is the region between the inverted parabola and the x-axis, okay, we got that, and whose vertical cross-sections perpendicular to the y-axis are semicircles. So you can draw a semicircle here, a semicircle there, a semicircle there, there. So those are all semicircles. Okay. So what for any slice that we happen to do here, again we're doing dy's here. So for every slice that you have here, you need that length as a function of y. Okay? Because that's going to be the radius of that semicircle. Okay? Well, we have y y as a function of x, we need to get x as a function of y. Because your x is going to be that radius. How far out the x-axis is, that's going to be the radius of the semicircle. Right? So the first thing, they've done it for you, but let's just see how they did it. We solved this for x. Okay, of course, when I go to do this, it's going to shrink back. Okay, so if y is equal to 4 minus x squared, solve that for x, which I would say add x squared to both sides, subtract y from both sides, and that gives you x squared is equal to 4 minus y, and then x is equal to the square root of 4 minus y. Be careful here, it is the positive square root because we're only doing this radius. This one over here would be the negative square root. Why mess with negatives if you don't have to? Let's just use that. Positive 4 minus square root of 4 minus y. Okay? So that's going to be the radius of that semicircle right there. Y is 0, this will be square root of 4, that would be 2. Okay? And when y is 4, that would be 0. So the radius would be 0. Yeah, so this is making sense. All right. So the next question is, what is the area of a semicircle? A circle is pi r squared, and a semicircle is half of the circle, so it'd be half of pi r squared, right? So this area of that semicircle would be 1/2 pi r squared. What is your radius? That's that length right there. So it'd be 1/2 of pi times the square root of 4 minus y squared. Well, what's the square of a square root? 4 minus y, exactly. So it'd be 1/2, well, let's just write that as pi halves times 4 minus y. Okay? That is the area of each of those semicircles. So what's our volume formula? Second? Okay, it would be the summation of all those areas, right? So that'd be the integral. Now the pi halves is just a constant, so let's get that out front, okay? And that would be from where to where? 0 to 4, because that's the limits on y, and that's just 4 minus y dy, because the dy is the thickness here. The area is that times the thickness at the volume of that one, and then you sum all those up from 0 to 4. Okay? And I think you've got it. The calculus is not the hard part. Okay? Doing the integral, that's the easy part. Setting up the problem, that's the part that makes it fun, right? Yeah, yes. Okay. What's that? Like circle, area of a circle is pi r squared? Yeah. If you need it, well, okay. Now, let's think back. This is a take-home test. You got your books. You got a lot of the formulas in your books. Any formula you can't in the book. You got the internet. You got all the libraries in the world, you know. Yeah, you can do it. Okay. And if you have questions, you can ask me. Okay. Not lazy questions, but good questions. Okay. All right. I might answer. Look it up. Okay. No. Okay. What's the integration of 4 minus y? 4y, y squared over 2, evaluated from 0 to 4. This will be pi halves times, which is 16 minus, second? Yeah, 16 over 2 is 8. Okay, and I'll do the 0 part. That's done. Okay, this would be pi halves times 8, which is 4 pi. And they didn't give dimensions on this one, I don't think, did they? Yes, that's exactly what they got. Good for them. All right. Any questions? Okay, how are we doing on time? I'm glad y'all aren't regular clock watchers, but we got a minute. Wish we could do this one. Not going to take much longer than a minute, but it will take a little bit. So we will begin next time with example 3. Really simple problem. Okay. This is a long section, though. Very long section. So homework exercises here. I think you can do any of the odds 1 through 7. I think you can do any of the odds 9 through 13. I think you can do 15, 17, 19, 21. So let's just say any of the odds, let's go back, 15 through 21. I think try to stop at 21 there. I believe so. And if those give you problems, we may cover some more next time. So it gives you a little bit to work on. And I'm awfully sorry I didn't get your test made out. Just a series of things. Hopefully this afternoon I will get it done. Are any of you on campus at all tomorrow? This campus? Not. You can pick it up Monday. That's fine. I was going to say if you're here either later this afternoon or anytime tomorrow you can get it, but do not.
I'm coming back from physics.
Oh, I see.
Yeah, 3:30.
Right. Okay. You come back at what time?
Around
3:30?
3:30. Yeah.
Okay. And you get through about 4:45 or?
Yes.
Okay. I'll probably still be here at 4:45, so you know where my office is?
Yeah.
Okay, yeah, you can go down there. Either y'all in physics too? All of you, okay. Hopefully, knock on wood, I'll have it done by then. But I just didn't happen to have a test prepared on just these 4 sections, so I'm having to make up a new one. So I will, like I said, I got started, but it was in Word, and that's miserable, so I'm going to start over in Word Perfect. Hopefully, sometime this afternoon I'll do. So see me after physics class. I'll probably still be here, and I'll see if I can get them to. Now, the only problem might be if I can get copies made. I'll try to get it typed up and copied before she leaves down there. That would be the only issue. I'll probably have it done, but whether I can get copies made. All right, good deal. Then y'all can have a good weekend working all these homework exercises and working on that test too. That'll make it a great weekend, won't it? All right, good dancer. All right. That ends the show. I'll discharge the markings and we will move on. And I'll stop the